And back at it again. Here we are. This one's going to start off a bit rough right out of the gate because you've got plenty of context to be able to manipulate and come up with some ideas for these. I want you to try and predict some reactions. So we've got 6 reactions up here. I will fully admit that 2 of them you probably can't predict unless you've actually done some reading already. That would be this one and this one. But go ahead and see what you can come up with anyway for those 2. The rest of them should fit within your wheelhouse. Officially, they aren't all acid chloride, so that makes it a little bit more challenging. But as we said already, that chemistry is the same. It's just varying levels. So you should be able to go through and work through these. So with that, go ahead and pause, see what you can come up with. And since you're back, I will really quickly scatter some of these out here. It's going to end up with the OH here. You wouldn't be able to do another substitution for that one. For this guy right here, it's got an interesting question of explain why you need 2 equivalents, which might make you think that this reaction is going to happen a second time. It does not. You really just get that structure. So that's an interesting why question, and see if you can come up with an idea for that and post it to Piazza. I'll just go ahead and throw it out there. I think that's going to be an exam question on the next exam. So somebody should attempt to answer that and get some feedback on it. We move to the next one, big old nasty drawing structure. And you might wonder why we have such large structures. And that's because a lot of these structures have, particularly the esters, have biochemical roots. And probably what we're looking at, in fact, now that I look at the structure, I can almost guarantee that these come from the isoprene unit backbone. And isoprenes make up the vast majority of our steroids and hormones and biological things. So if you've ever seen like the cholesterol structure, which I might be getting close enough to write. I think I might have missed a ring. That general structure comes from linking together a bunch of isoprene units. Okay, so just interesting trivia there. The next one, which I said you were probably going to struggle with, super interesting, and we will actually talk about it in this lecture video. It's known as the Baeyer-Villiger reaction. For those of you that think Bayer as in Bayer aspirin, no relation. It is a relation. That's actually exactly where it comes from. He's the guy that discovered it in his synthesis of aspirin. The next one, which is also kind of equally challenging, but I would argue potentially easier if I'd shown all the reagents. That would have made it a lot easier. One of the things that might have also made it easier is if we'd switched it around to say PCl3, Br2, and then H2O. We did need 2 steps there. We did need the H2O present. Oh, actually, no, we didn't for this one. But it's easier if you look at it with those reagents. So if you wanted to try it again, now's your time to try it. And when we come back, you're like, oh, did it do anything? Yeah, it did. Put a bromine there. That's it. And then the last one, right over the top of my weird looking picture, so we'll just erase that because that wasn't all that important anyway. Draw that out. 1, 2, 3. And there we go. Technically, with that one, we would also have that piece coming off. Later, we'd acidified it. So there are all those pieces. If you've got questions about those, that's exactly why we have Piazza. We'll talk through some of these. But again, you should have been able to pick up the vast majority of those just based off the pattern recognition that we've already talked about. If you're, again, locking onto it, I didn't see that exact reagent, you're right, and you won't, and the exam is going to suck. So try and look for those patterns and follow the pattern recognition, and that's going to help you out a lot. Okay. So you will encounter some named reactions for nucleophilic addition eliminations. In this case, I'm referencing the transesterification and saponification. And these are really just kind of historic names, and as far as names go, they could be worse. Trans, as in we're switching it, we're changing it. Trans ester. So if we go through, here's our ester with a carbon and a phenyl. We look at the product, we have that same oxygen and the phenyl, but now instead of a methyl, we have a T-butyl. So we've changed the ester, transesterification. Here's where I would get upset with the names. We can then also go to saponification, and when we go through saponification, we start with an ester, and we end with kind of the same root, except now we have, instead of a carbon out there, we have a hydrogen. So it's not really an ester, so we can't call it a transesterification, but the chemistry of both these reactions is identical. Okay? Your negative strong nucleophile coming in, attacking nucleophilic addition, elimination, all the jazz. Same process. The saponification becomes a famous one because that's soap. If we run this under basic conditions, which we do, but instead of isolating the acid, okay, by acidifying it, we get rid of that last step, and we're very careful with the amount of base we add, we'd have a negative charge structure. We have a polar negative at one end, and then we have a non-polar CH3 at the other. Right? So polar dissolves in water, non-polar dissolves dirt and grease. This is effectively a soap molecule. That said, you have to have a significant portion of both those pieces. That polar part being really, really charged dominates the overall intermolecular forces for that compound, and so it really only dissolves in water. The non-polar part is crushed. So what you would need to do is add a few more carbons, and I think it's 6. 1, 2, 3, 4, 5, 6. A 6 carbon chain is the optimal length, and what you now have is a standard soap molecule, okay, with a non-polar portion and a polar portion. The saponification also becomes super relevant when we're looking at fatty acids and, say, lipid bilayers, say in biochemistry like cell walls. Right? So that whole structure owes a lot to organic chemistry and the saponification reaction. Okay. So again, those are kind of standard. I don't like spending a lot of time on it, but we'll go through and look at the transesterification reaction. This time I'm going to do it under acidic conditions because the acidic conditions are less straightforward, or really just less is a better way of saying it, because I think it's straightforward all the way through. It's just there's less. So under acidic conditions, the primary thing you need to neutralize would be an acid, okay? Which means the reactive thing is going to be the lone pair electrons on your carbonyl. That will come out, pick up the hydrogen, shuttle the electrons to our alcohol. The result of this is we would now have a positive charge on that oxygen. And of course, oxygen does not want to be positively charged. So we end up with a resonance structure where those electrons get withdrawn from the carbonyl. That becomes important because that now establishes a very strong electrophilic species because of that positive charge. At this point, we would go out into our environment to see if we had any source of electrons to stabilize it. Okay, this reaction set us up with it. Note you've got the parentheses around that saying there's 5 CH2s. Before you get super excited and start drawing this in as a negative oxygen. The problem with drawing it as a negative oxygen is that would require basic conditions, or acidic conditions, so it has to have the hydrogen still connected. Those electrons can then go up and attack. We would then have our tetrahedral intermediate. It's going to take a little bit to draw here. With this tetrahedral intermediate, we're going to have that positive charge on that oxygen. Oxygen does not want to be positively charged, so it's going to withdraw electrons from the easiest place for it to get them. Okay? For those people that are like, well, I don't know what's easiest for it. Okay? Well, as a hint, for that oxygen, there's 3 places that it can get electrons. 1, 2, 3. If you don't know, you need to draw 3 reactions from that point and show what the result would be if it had removed electrons from those points. As a hint, for that first one, it's the reverse reaction. Okay? For position 2, it results in an incredibly unstable structure, and for 3, what we end up doing is removing the hydrogen. That is an equilibrium arrow because it is an equilibrium reaction. We would then have regained our lone pair electrons, and we would have something akin to the acetal that we learned about before, except in this case we have 3 oxygens. That is incredibly unstable, and it wants to fall apart. Okay? And there's lots of ways it can fall apart. Again, 1, 2, 3. Okay? So you should be able to evaluate what would happen if each of those positions fell apart. If one broke off, we'd end up with an acetal. And as we know back from our last unit, acetals are not particularly stable, and in the presence of our alcohol would probably just end up reverting back to this tetrahedral intermediate. If we go through and break off 3, we end up only doing the reverse reaction. Okay, so that's not particularly productive either. Okay, so we really need to attack 2. The problem with 2 is that if we tried to have those electrons leave, that would leave as a negative, and that's not particularly stable. So what has to happen is we need to protonate yet again. When we go through and protonate with our OCH3, now with our hydrogen, that oxygen would again become positively charged, which it does not want to be. To fix that, what can it do? I know that looks awful. It can now act as a leaving group. To help move it along, our top oxygen could shuttle electrons towards it, and we could go through and show a potential result. OCH3, H. We would have a positive charge on that oxygen, and our other oxygen that left the structure would have picked up its lone pair. Okay? A lot of people don't like that positive oxygen, so instead of having that top oxygen come down, they would just have the OCH3 leave on its own. If you did that, the structure that you would end up with would be this one. And that structure is merely a resonance structure of the one we drew. If you're to draw a good mechanism, your mechanism should end in the black version, not the blue version, because the blue version is a bad structure because we're missing octets. It may give us charges where we want to see them, but we don't have the proper octet, and that's technically bad. Okay? We can still work from it though. We need electrons, so these electrons could come back down. That means something remotely basic in the environment would need to come in and pick that up. And what we would end up with would now be our final structure, our new ester. And 5 became 9 as I went through and did this. our new structure with the new ester functionality. One common thing that pops up is trying to track these oxygens. So let's see if I can go through and do this. Let's not do it with red. We'll use purple, green, and I think I can get away with orange. You will commonly see people go through and ask questions on where those oxygens ended up. If you understand the mechanism, you can track where those oxygens ended up. If you don't understand the mechanism, you end up shuffling where the oxygens ended up in the end result, thereby getting the question wrong. And there's only so many permutations, and those permutations happen to match pretty closely your multiple choice options. Okay? So you should be able to move through your mechanism to see how those oxygens came on and off the structure. We are not talking about changing the CH3s, those carbons, because those bonds are not easy to make. What we're talking about making and breaking are in there. Okay? It's that ester bond that connects it, because we have that large positive on that carbon. Okay? And that's what's driving it. That's our reactive bond. Okay? So with that, I talked a whole lot about that mechanism, more so than I really wanted to, because it's just a long one. Lots of acid-base steps. You're just trying to make sure that it stays in the acidic environment. Okay? Which gets us to the next one. This was that weird, goofy one that I showed earlier, and you probably were like, what the hell happened there? It's known as your Baeyer-Villiger oxidation or Baeyer-Villiger rearrangement. You're taking MCPBA with a ketone, and that somehow inserts an oxygen into that carbonyl carbon bond. This particular example that we'll walk through is a little bit easier because it's symmetric. If we look back at the problem that I had you go through and do, it was an asymmetric ketone. And it turns out that the group that migrates, and we'll address that migration here in a second, is dependent on certain features. So in the case previously shown, it was a methyl versus a phenyl. The aryl group is that phenyl has a higher migratory aptitude than the methyl group, which has the lowest migratory aptitude, which means we would expect the oxygen to insert into the phenyl carbonyl bond, not the methyl carbonyl bond, given the choice. Okay, so what's going on with this? We've kind of seen something similar in lab with the Julia-Cologne epoxidation, I think is what it was. Julie Cologne, something like that. Our oxygen from our peroxy structure will come in and attack. We get our tetrahedral intermediate, and then everything goes sideways. Okay, so let's try and draw that out and see what we could envision within that. So we've got our phenyl, oxygen negative. We've got a phenyl, oxygen, carbonyl, yada, 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 hydrogen. When these electrons come back down, we would want to somehow break something. Okay? We would exceed the octet. The answer that we've been showing is that we eject the leaving group. Okay? So oxygen being the most electronegative of those, that would make sense, but that only takes us backwards. Okay? So we could see a reason why this might get named, because wouldn't we expect the oxygen to leave? And instead, what quote unquote leaves, and because I'm drawing, you can't see my finger air quotes, the phenyl leaves. So one of these groups out to either side leaves. But that's not stable. Okay? And because it's not stable, it can't leave, quote unquote, very far. And really what it does is it just shifts. It does a rearrangement. But for us to do a rearrangement, one of our other atoms would have to be moving around as well. And that's where we go through and note the high reactivity of that oxygen-oxygen bond. That bond is dying to break apart. Okay? much like what we saw with our epoxidation reactions. Okay? So what can end up happening is that our phenyl, as it shifts to the oxygen. Okay? And I know that looks like a mess, but if we draw that out, it really isn't all that bad. There's our carbonyl. What happened to the phenyl? Well, that bond no longer exists. There's the bond to the oxygen. The bond that I have is now here. And if we do some kind of flippy doodahs with this, what do we end up with? Oh, well, that's just an ester. And that's exactly what happens, right? You've inserted the oxygen into that bond. It is a really neat reaction, okay, that this would actually happen. And astonishingly, look at the yield. I mean, 100% yields. These are phenomenally precise in that reaction. So again, if we walk through it, one of the things to note is you see that CF3 as I'm pointing at the screen. It's freaking stupid. Down here, CF3SO3H, you might remember that as TFOH. That's our triflate. Okay? That triflate is a strong acid. And what happens is that strong acid goes through, activates the carbonyl for nucleophilic attack. So we get the protonation. Now our epoxide can come in and attack, breaks that open. We can get our triflate deprotonating that, which I kind of ignored. Okay? And now kind of the fun part is that reformation of our carbonyl and now that whole shift, okay, that rearrangement. And that's largely because that MCBA or the metachlorobenzoic acid now is a phenomenal leaving group due to that resonance, and it kind of just shatters off, leaving you with effectively your final ester. Okay? It is under acidic conditions, so that carbonyl would have been protonated, so you have to deprotonate it, not that big a deal. But you've now done your reaction, and you've inserted that. The big deal with this, though, is the asymmetry. So when it's symmetric, you just do the shifts, insert. Fine, memorize that. And in fact, I would argue memorizing that. Okay, just Baeyer-Villiger, you see the peroxy reagent, and you see a ketone, insert an oxygen. Done. The next thing that you have to memorize also is that migratory aptitude. That gets frustrating, and I don't have good answers for that. I've watched a couple other lectures and read some papers, and I just don't really agree with the statements being made. Ultimately, you need to have it memorized. Okay? So hydrogen, awesome at migrating. It's then the phenyl group, then tertiary, secondary, then primary, and then methyl or zeroary. Okay? But that's our Baeyer-Villiger oxidation, or as I like to call it, a Baeyer-Villiger rearrangement, or just, shuffle stuff up. Last one, Hell-Volhard-Zelinsky reaction. And as you saw at the beginning of this lecture, there are a variety of ways that you can organize those reagents. Okay, and that's a bit frustrating. I really just put it out there because I wanted you to be able to see that, but be aware there's other ways to set this up. First things first, we have to address the chemistry that we see. So, come on. Oh, this will be our last slide for the record. And apparently I lost my connection. Okay, so we've got an acid. Br2 is an electrophile, and I guess we could color code this. PCl3 seems a little bit weird. That P, if we remember back from Unit 1, is an electrophile. And then we've got water. Man, I'm not color coding to save my life very well. Electrophile. Electrophile. And then we have water, which can pretty much do, well, anything. Okay? So it doesn't help us a whole lot. So this is where having some command of memorization could help us out. Our PCl3 is an electrophile, similar to thionyl chloride, converts all OHs into halogens. So that PCl3, we should recognize immediately takes a hold of that OH and converts that out to a chloride, okay? Or a bromide, it ultimately doesn't matter, and you'll see why in a second. And then we've got Br2, which is an electrophile. Well, for an electrophile to react, we would need a nucleophile. We would need electrons. Well, right now, all I see is an electrophilic carbon, right? And even up here, at best, we had an electrophilic carbon too, but the acid kind of dominated that chemistry. Well, the interesting feature of this is to get, or to convert that structure into a nucleophile, I would need a negative. The easiest place to get a negative would be to remove electrons, right? Or sorry, remove a positive charge. Removing chlorine doesn't help, removing oxygen doesn't help, which means what I'm going to have to remove will be hydrogens, and in particular, just one hydrogen. If I remove that one hydrogen, I would then have my nucleophilic carbon, which could indeed then react with the bromine. And that should look really familiar because that's our haloform reaction. So phenomenal, that could put a bromine on there and we could be progressing forward. That's starting to look an awful lot like where we ended. Right? But why would that hydrogen be acidic? Right? Well, it's acidic because chlorine is electron withdrawing. It doesn't do a very good job of inductively donating electrons into that carbonyl. If anything, it withdraws them due to its electronegativity and its inability to really form more than one bond. That means that those hydrogens, and in particular those alpha hydrogens, would be acidic. Well, why did I not remove those outright up here? Well, up there, that oxygen donates electron density in, making those hydrogens less acidic. The carboxylic acid alpha hydrogens are not acidic. But if I moved the acyl chloride, they now are acidic. That's a pretty huge distinction that is being taken advantage of in this case, right? That acknowledgement of representing that difference in reactivity is likely why this ends up getting named, because who would have thought of that? The next part that kind of goes with this is that we've now done our standard kind of haloformish type reaction. We now have the bromine, but that's not where we end. Well, this is where we add our water. The water can now come in and attack that electrophilic carbon. That carbon, carbonyl carbon, is more electrophilic than the green one because we have that pi bond connected to it. So we end up going through and doing nucleophilic addition elimination, and it takes us back to the carboxylic acid. So this reaction is neat because I maintain the carboxylic acid functional group while also adding some electrophilic characteristics with the bromine hydrogen substitution. Okay? So that's pretty cool behind the Hell-Volhard-Zelinsky. That chemistry is all within your wheelhouse and you have the ability to do, but there's some very subtle differentiations within that make it tricky, that it might make sense to just straight up memorize this one as a named reaction and just memorize the end result of this. Br2, our phosphorus, we end up doing a substitution of a hydrogen for bromine, very similar to the haloform test. Okay. And with that, as we already kind of alluded to, we are actually done with this sequence. So I hope most of that made sense. If not, this is why we have office hours in Piazza, and I look forward to talking to you then. Have a good rest of the day.